Thanks. So first of all, thanks the organizing for inviting me. This is very special because it's the first time that I've been invited to talk in a workshop. So this has to be cool. So yeah, we have been talking about rotation, a little bit about magnetic field, but we haven't talked about composition gradients. So that is what I'm going to talk to you about now, about compositional mixing in gas giants. I will show you some of the toy models that I've been doing to try to understand these objects, the interiors of these objects. It's on? It's off? I don't know how it works.
Last time you came out of the room.
It's not mute.
Oh, that's it.
It's not mute, and it's good.
Okay, then it's good. Yeah. But before talking about science, I want to talk to you about something that is more important for me, which is my group. So this is our group at CU Boulder. And if I counted correctly, there are 11 people here. Sorry. Everyone here works on different problems related to astrophysical and geophysical fluid dynamics, and we have a lot of fun. We have postdoc students, more senior researchers. We have a diverse group, and I value that a lot. And something that I wanted to mention is that this group is large, and the reason for that is Kit Julian, because Kit Julian opens the gate for all of us in the applied math department. We gather every Wednesday at 11 a.m. in the morning to discuss about all sorts of problems, and that wouldn't be possible without Kit. So yeah, I could say a bunch of things about Kit. I didn't have the chance to work with him, but I had the chance and the pleasure to have him almost every day in my office. And yeah, he was a brilliant guy. He was remarkable in many dimensions. But perhaps more important for me is that one of those dimensions was that he cares a lot about the grad students and the postdocs. When I moved to Boulder in 2021, following my wife at the middle of my PhD, I didn't have any scientific reasons to be at CU. And I was very depressed, like walking around campus, trying to work from different places. I didn't have an office, anything. And I show up in Brad's group to talk about my science. Kit happened to be there, Nick as well. They started to invite me to their group meetings. And Kit Julian immediately started to care about me. And he made sure that I had all the resources to finish my PhD remotely. So he gave me all the support, as long as with Brad. They even gave me computational resources to do simulations. So wherever you are, Kit, grateful forever. OK, let's go to talk about science now. So yeah, I said I'm going to talk about gas giants and composition gradients. We have a diverse group, so I thought that the best way to start with this is talking a little bit about gas giants from the basics. So unlike the rocky planet, like the Earth or Mars, the gas giants are mainly composed of hydrogen, helium, and a much smaller amount of heavy elements. We don't really know exactly how much is the abundance of heavy elements, but it's roughly 10% of the planet or so. So some people call them gas giants, but I would say they're liquid giants because maybe about 90% of their interiors, it's in the state of metallic hydrogen, because the pressures are so high as you go deep that the electrons in the hydrogen get released and they move freely. They are the largest planet in our solar system. If you take Jupiter and Saturn and you weigh the mass and you compare with the whole planetary mass that you have in the solar system, they account for about 90% or so. So they definitely govern the dynamics of the bodies, especially the smaller ones, together with the sun, of course. Oops. They also form early and really fast, like within millions of years. You form rocks, you accrete rocks, and when this bigger rock has about 10 Earth masses or so, you accrete gas, and that happens really fast. So that is why they are big, they are massive. So in some sense, the Earth, the Mars, and all the other planets in the solar system are just the leftovers of Jupiter's formation in particular. So because of that, We said that the gas giants are a window into the history of the solar system because they formed first. So if we can understand the evolution of them, then we can maybe extrapolate back and see what were the conditions of the protoplanetary disk that gave birth to the solar system, actually. So the gas giants, we have seen plenty of images and movies within these days that shows this sort of things. They have symptoms of rotationally constrained turbulence. As you can see here, we have winds going in different directions. There are some vortex in there. And if you look at the poles, at least in Jupiter, you can see a bunch of vortices surrounding a central one that is bigger. I think in Saturn you see hexagonal parts and more complicated features. So all this is showing us that rotation matters for these objects. And we can do a lot of, we can apply our expertise to understand these objects. So that is the stuff that is happening at the surface in the outer layers. But I can assure you that there is also really nice stuff happening in the interiors, which is also very interesting. So because of that, I'm going to introduce you briefly what is the internal structure of these objects in a cartoon way, so not too complicated. So 30 or 40 years ago, the internal structure of a gas giant looked like this cartoon. Basically, you have a dense core made of heavy elements. And for those of you who are not familiar with heavy elements are, for astronomers, all the elements heavier than helium, okay? So yeah, you have a central dense core, not solid, because for the conditions in the interiors of these objects, the silicates and the ice could be in a liquid state. And surrounding this core, you have a hydrogen and helium envelope. And the whole point is that 30 years ago or 40 years ago, people thought that there was this sharp transition between the core and the envelope. And of course, the envelope was fully convective. The heat transport was efficient, large-scale convection, and efficient cooling. All of that was fine until the Juno mission. So Juno, which is a spacecraft that was launched like in 2016, and I think it's still ongoing, I'm not sure, went to Jupiter, took measurements of the gravity fields on polar orbits, and it turns out that if you want to fit the gravity of the planet, you cannot have that dense, centrally located core with a sharp transition to the envelope. You need to have something more like a fuzzy core, meaning that the core, these heavy elements, are distributed over a gradient. That's all. That is what Juno is telling us.
How do you determine that from a remote measurement of the gravity?
Oh, that is a good question. I think I don't. So basically, you can decompose the potential of the planet, something like this, a symmetric part, and then you have a bunch of harmonics, gravitational coefficients, okay? This can be a function of latitude and I don't know, whatever, okay? And if you track I think the spacecraft send a radio signal, and you can track motions in the spacecraft itself. So you can measure the J's, okay? And you can also get the J by integrating over the density. And actually, this illustrates the problem because we can measure the gravity coefficients, but we can also express the gravity coefficients in terms of an integral of the density. So there are many possibilities for the density that can give you a match, a fit to the gravity. And I will actually show you that. Okay, but this is for Jupiter. The same was inferred for Saturn, but not using this method. I think that was done by Jim Fuller and Chris Mankiewicz at Caltech, where they did seismology in the rings. They also conclude that the interior of Saturn is about 50 or 60% established stratified, fuzzy core as well. So why this is important? Well, there are many reasons. One is how can the gradients can survive over the age of the solar system? You're from the planet, you let it cool down for the age of the solar system. That is 5 billion of years or so. How much is the age of the solar system? Yeah, right. You from the planet, it burns really hot. So you will expect that convection get rid of any primordial gradient. So how can the gradient survive for such a long time? We don't really understand that yet. From another point of view, composition gradients can stabilize fluids against convection. That can affect the cooling history of the planet. You can form layers. You can suppress convection. Composition gradients can affect this in many ways. And for the people that like magnetic fields, so how a dynamo can operate when you have a fuzzy core, a composition gradient. I don't think we understand how dynamos work in that sense, even in layered convection.
So if you can back out fuzziness of the core from the modes that comprise the gravitational field, can you use the modes that comprise the magnetic field to figure out whether it's produced primarily inside the fuzzy core or outside or across the fuzziness? Is it known?
I think that is a question for how.
Okay.
For how.
Well, the short answer is if you just do an estimation of where the outer boundary of the dynamo is, still pretty shallow. Let's say 80% or 90% of the Jovian radius.
Okay. Okay, thank you.
Okay, so fuzzy cores or composition gradients are challenging, and I kind of show you that within that stuff that I wrote there. So this is a plot that shows you the mass fraction of heavy elements, the abundance of heavy elements, as a function of the coordinate mass within the planet. Sorry about that. This should be radius if I made the plot in a different way. But this is the surface. This is interior. This is data. These are different profiles that you can infer from Juno. Depending on how you cook the planet, what are the assumptions that you have, the equation of the states that you use, you can get different solutions for the distribution of the heavy elements, which is essentially what I wrote here. We can fit the gravity with different densities. And that is a problem because it's degenerate. But there is a consensus, I think, in the community that this core has to be extended to some degree. So yeah, and so far there are no formation models that can give you something like that after evolving the planet for the age of the solar system. So I'm going to show you a movie. This is from one of my colleagues, Ankan Sur at Princeton. He's working with Adam Burrows on this. And yeah, the same. The mass fraction of heavy elements as a function of the normalized mass. This is the surface, this is interior. There are 3 models here. All of them start with the same distribution of heavy elements, but they have different entropies. You can think about this as the blue is colder and the green is hotter, the interior, okay? So I'm gonna let this, and you can see how this evolves. So basically, what you have is, you start with some primordial composition gradient, you let the planet cool down from the surface, you drive convection from the surface, and this convection some propagates inwards. And depending on how much energy you have, actually, you can get rid of the gradient entirely, or you can stabilize the interior. You can have either a continuous distribution of heavy elements, or the gradients can break up into different layers. So that is how a 1D model evolves, essentially, roughly. So if you think about fluid dynamics, this is kind of this is very similar to a problem of penetrative convection, when you have a convection zone on top of a established stratified region that propagates inwards. And maybe you can form layers underneath. So because of that, I think that we as fluid dynamicists can contribute a lot to the understanding of this.
The one before, well, you might get into this later, but does it make a difference if you allow for helium rain to be formed higher up? So if you have more shallow layers happening as well, or?
Yeah,
separate.
I think that doesn't have a significant effect
What happens further in the core?
with what happened further in the core. Yeah. There was a paper by actually Ankan Sur, a LabJ letter recently, where they incorporate the helium rain, and they have fits for both Jupiter and Saturn. Same. You need to be cold if you want to preserve the gradient. If you start hot, which is what usually you get from formation models, you get rid of it.
Yeah, I would expect maybe the same end result, but I would expect the process to be different, right? Because if you have a more shallow layer that's also trapping, or making heat loss less efficient, then would the time scale, like the timelines, would shift a bit, right?
Yeah, but I think the conclusion was not
ultimately,
in a
yeah.
significant way.
Yeah.
So yeah, how can we study this from the point of view of numerical simulations like multi-D or MHD? That is a really hard problem. So I have faith in the lab experiments, actually. And because of that, I want to show you this, which is this is a classic experiment by Turner in 1965, where he can actually capture both of the physical situations that I just described to you: penetrative convection and the formation of secondary layers. This was done with salty water. So basically, he started with a fluid at isothermal, initially uniform temperature, and there was a salinity gradient, linear. The fluid was more salty at the bottom and fresh at the top. And I think that what he did was heating the tank from below, but I flipped the image to make you think that he cooled from above, just for convenience. So basically, you have a convection zone that starts to propagate to the bottom of the tank, and eventually you start to see the formation of secondary layers. And you can keep running the experiment, and the whole thing is going to mix. So yeah, this was done with salty water. The Prandtl number was 7, and the ratio between the salinity and the thermal diffusivity is 10 to minus 2 or so. So yeah, one of the important results from Turner was at which speed this convection zone propagates inwards. So to do that, he basically made some conservation arguments. He assumed that the rate of change of the heat content within the layer was set entirely by the flux that was cooling the layer at the top, and that the salt that you had originally in the layer was just, you just changed the distribution of the salt from a linear distribution to be fully mixed. So you conserve solute, basically, within the layer. So if you do that, you can have a differential equation for the size of the convection zone, H, and you can integrate that to see how it moves over time. So yeah, the interesting part here is that he found two solutions depending on the conditions of the interface. So this is the solute step at the interface. This is the temperature step at the interface. And depending on the relative contributions to the solute step and the temperature step to the density across the interface, the value of this density ratio, that he called it, can give you a different prefactor. So one of the limits was that if you look at the interface and you measure the density, if the density is marginally stable, meaning that the density jump is 0 across the interface, then this is 1. And that means basically that the mixing happens because the fluid right underneath the front, it's Leduc unstable to mixing, basically, or Rayleigh and Taylor unstable to mixing. And the other assumption, which is what I think is the correct one, was that if you assume that all the potential energy released during the cooling is used to do work, leave material and mix it, which is entrainment, then you get R rho is 3. I think that in his experiments, he didn't measure a density jump at the interface, but Fernando in 1987, he repeated the experiment, and he found a jump, a clear jump. People repeat this with numerical simulations, and you also see a jump at the interface. So I think this is more correct than the other. So anyways, you can solve for the size of the convection zone, and you get this classic scaling that the front moves as the square root of the time. If you increase the flux, it's going to go faster. If you increase the gradient, it's going to grow at a slower rate because, again, the salinity gradient stabilizes the fluid against the convection. So what about the secondary layers? Something that is really neat here is that these layers form in the usual way that we used to think about convection. And I'm going to explain that in a second. You basically have this front that is moving down. And right underneath the front, you have a thermal boundary layer and a solute boundary layer, if you want to think in that way. And what happened is that this thermal boundary layer grows over time. And eventually, it becomes unstable. And you form a second layer. Then below that second layer, you have exactly the same. You keep forming a thermal boundary layer that grows over time, and it becomes unstable, and you form a second layer, and so on. This has nothing to do with double-diffusive instabilities, as the papers by Timur Radko or Pascal. This is a different mechanism. So in other words, you look at underneath the front, you check for the thermal gradient. The composition gradient stays roughly the same to the original one because the chemical diffusivity is much smaller. But the thermal one, it's evolving over time. So eventually it becomes unstable and you form a layer. That was done for Prandtl numbers of 7, but during my PhD, I repeat the experiment at lower Prandtl number. Exactly, I did exactly the same experiment with numerical simulations. I used Daedalus in 2D, and I did this for different Prandtl numbers. And I'm showing you on this plot the size of the convection zone as a function of time. I think those are 3 simulations. In green is Prandtl 7, in blue is 0.1. And I put the theoretical predictions for the 2 limits that Turner found. And you can see that the answer lies like in between. But it's still a T to the 1/2 entrainment law. So it seems that the Prandtl number doesn't matter much for how the front moves as a function of time. But you can have different prefactors, actually. So one of the things that we did is that I extended the analytic model of Turner and Fernando, and I actually incorporated heat flux that comes from below the layer. Because you are cooling, you have hotter fluid below, so there must be some flux coming from the other part, not just from the top of the layer, which is this epsilon parameter there. And I also considered that the entrainment efficiency, meaning that it's not necessarily true that you will use all the energy released during the cooling to do the work and mix the material. There must be a fraction. It's not perfectly 1. And actually, I can recover Turner's result. If you assume that the flux from below is 0, then you have 1 plus 2 gamma. And when gamma is 1, that means the efficiency is perfect. So you get R rho equals 3, which was Turner's one of the limits in Turner. So anyways, we study the propagation of the convection zone, and we also look for layers. And we only found layers for Prandtl number 7, just as in the experiments. And the reason for that is that at low Prandtl number, in my experiments, the efficiency of the heat transport was so high that any thermal gradient that develops below the main convection zone is really small. It never becomes thermally unstable to convection. So I didn't find any layers. That was one way of looking for layers, but you can also develop layers by double-diffusive instabilities. which is briefly summarized in this scheme here. So you basically, depending on the Prandtl number and the diffusivity ratio of the flow and the internal structure of the fluid in the sense of the compositional stratification and the thermal stratification, you can excite different different modes of the double diffusive instability. That depends on this parameter, again, the density ratio. So if the density ratio is 1 or small, the destabilizing effect of the thermal stratification will cause overturning convection. And if it is larger than 1, that means that the composition gradient is stronger than the thermal part. So you can be, in other words, in terms of stellar astrophysics language, you can be Schwarzschild unstable, but Leduc's stable. So yeah, I think that for the gas giant, the limit is 50 or so for the Prandtl number and tau. But we don't really know what is the internal structure of the planet. So we don't have an exact value for what is R rho, for example, to know if you could fall where you could fall in this regime. But what is important here is that when you excite double diffusive instability, you have two options. If you are too stable, wait a second. If you are too stable, you can just have a mode that is called homogeneous oscillatory convection, where you basically have an enhancement over diffusion, but it's still weak, not much transport. And if you are not that stable, then you can develop layers, spontaneously formed layers, actually. But that boundary, I don't think it's clear. We don't really know how to get that from first principles. It's very easily to develop layers with simulations, making the right gradients, but in nature, we don't really have a sense of how to compute that. You had a question.
A question from oceanography. You have stratification by temperature and salinity, and they're opposite to each other. But the thermodynamics of the system is such that they're trying to compensate each other, and you will not see this in the density gradient. Is it something similar possible in your system?
I didn't get what you asked. What do you mean by not seeing in the density gradient?
Temperature gradient and salinity gradient, they both affect the density gradient.
Yeah.
They're compensating each other in the water, so that the gradient may be constant. It will not see the gradient of temperature and salinity because they compensate each other. Is something similar possible in this system?
For the gas giants,
Yeah, for example, your R rho will become equal to 1.
oh yeah, but if R rho is 1, you don't get layers, right? It's fully convective in that case.
Yes, so you will not have layers.
I don't think that is the case, because with Juno we are inferring that the planet is not fully mixed. If R rho would be 1 in Jupiter or Saturn, then the envelope would be fully mixed. No gradients of heavy elements.
So it doesn't happen.
So I think that is not possible. It's not consistent with the data. Sorry, I didn't get your question at the beginning. Okay, so you can excite the layers, you can develop the layers, but there is a problem here. And I think that we don't really understand this yet. And the problem is that you form layers very easy, but they merge. And they merge really fast. And if you want this to work in a gas giant, for example, these layers, again, need to survive for the age of the solar system. And at least all the simulations that we have so far are Bose-esque, and all of them exhibit this sort of behavior. You form the layers, it just makes. So yeah, hard.
What is R rho for these?
For this, I think this is Prandtl number of 0.1, and the tau was also 0.1. And I think that rho in this one was 1.25, which is close to the, it's in the regime where you form layers, actually. And I think that for this sort of simulation, Pascal and her group back in those times, they estimate like the critical density ratio at which will form layers for Prandtl 0.1 and tau 0.1 was about 1.5. So it's close. So yeah, a problem. So if convection is too vigorous, why the gas giants are not mixed? That is the question that I've been trying to understand. And one possibility, we have learned in this workshop that rotation hampers convection, right? That it inhibits the heat transport. So maybe rotation can have some effects on the propagation of this convective front or the stability of these semiconvective layers. So that is the whole point of this talk. So yeah, we know that rotation affects convection. It suppresses the heat transport. And just to get an idea if this is worth to have a look, with numerical simulations, I computed some order of magnitude calculations for the velocity using mixed length theory. And these are for Jupiter using a flux that is in the deep interior of the planet. We want to do the mixing in the interior, so I should not use the flux that is near the top, which is much larger. And I took these values for a situation when I think it's about 10 to the 6 or 10 to the 8 years after the formation, where the luminosity was high enough to cause significant mixing. If we take Jupiter now, for example, and compute these velocities, they are going to be really small because the luminosity of the planet has dropped significantly over time.
How do you know the thermal expansivity of the interior?
Well, we have material. That is actually a good question. I think that the more serious attempt to understand the material properties is with, how is it called? Ab initio, yeah, molecular dynamics. You put a bunch of atoms at a high pressure and temperatures, and you see how they move and those sort of things. That is how we get the diffusivities, actually.
What's H here?
Oh, H, sorry. H is a pressure scale height, but near the center. So it's about the size of the planet, actually, a fraction of the size of the planet.
Fraction, or so it's much less than.
It's much less than, yeah. Yeah, close to, deeper in the interior, it's about the radius, actually. So yeah, this is without rotation, and I took the scaling from your paper with Keith and Susan that you can get from the CIA balance, and if you plug the same values for the same flux, you get a reduction in the velocity of about a factor of 6 or so. So it's not that big. You can think, oh, this is not even an order of magnitude. It's smaller, so rotation doesn't do anything. Why are you smiling? Okay.
You can see where it's going.
But this is not significant for the velocities, but it's significant for the mixing, because in the usual way to understand this entrainment process and the propagation of convection zone, what really matters is the kinetic energy flux available for convection. So this is an hypothesis that was proposed in the 70s, the entrainment hypothesis, which tells you that the rate of change of the potential energy due to convective mixing, because I'm lifting material from below, I'm mixing it within the convection zone, that energy needs to come from somewhere, right? And that somewhere is the kinetic energy flux of the motion, which is the velocity to the power of 3. So if we have an order of magnitude difference in the velocity for mixing, this is 3 orders of magnitude. So it could be significant. So yeah, the other thing you can do is you can compute the kinetic energy flux for the rotating case and for the non-rotating case using the prescriptions for the velocity and relate those two with the Rossby number. And I know what you're gonna, what are you gonna ask? So this is the Rossby number that you can compute using H and the rotationally constrained mixed length velocity. You can use the free fall velocity and you will get a different scaling, but I like the rotationally constrained. So yeah, for Jupiter, I think that if for the values of the flux, and H and omega, which is omega, I think Jupiter rotates roughly once every 10 hours or so. The Rossby number that you get for the previous parameters it's about 10 to the minus 6 or 10 to the minus 5 or so. That is quite small. So that means that the kinetic energy flux available to do the mixing is the square root of the Rossby number, smaller than the kinetic energy flux available in the non-rotating case. So that means that we have a reduction in the energy available of about 2 or 3 orders of magnitude. So it can be it could be significant.
Yeah. Can I ask about the age, right? I mean, the age is an important factor here. How do you determine what's the value of age here?
Oh, for now, just to give you an idea of the numbers, I'm just using the pressure scale height that is deeper into the planet, because that is where you want to do the mixing. I see your point that if you have layers, let's say, and H is small, then maybe it's not rotationally constrained. But it's not, you don't know for sure if you have layers. You can just have an envelope with a stable
It's a huge
region.
unknown, right? H is a huge unknown.
Yeah, it's unknown, but I'm assuming that it's the pressure scale height, okay? You need to assume something, right?
There is another factor, sir. You're talking about rotation, but you may also have Rossby waves, and they may have tremendous effect on the mixing.
Yeah, I'm not even thinking about Rossby waves. Sorry.
I will show it in my talk.
Okay, so from the calculations, that could be misleading. I agree with you. It seems that maybe rotation is important for the mixing, and so it's worth doing some numerical simulations. So from that point of view, the gas giants are very complicated objects. They are low Mach, rapidly rotating flows. They have density stratification. We haven't talked about density stratification at all in this workshop, and that really matters. About density scale heights or so. They have many species, hydrogen, helium, heavy elements, and they have magnetic fields as well. So it's really complicated to simulate gas giants in a computer. So we have to, personally, I limit myself to local models and toy models and try to understand something and then move on to more complicated things. So just to give you an idea of the dimensionless numbers, for Jupiter, if you use the flux, I think the Rayleigh number is about 10 to the 24, Rossby number 10 to the minus 5 or so, and the Pratt number and the diffusivity ratio is 10 to the minus 2. So from the point of view of the microphysics, I think it's fine. We can do simulations in this regime, but I'm not sure if we can reach that level of Rayleigh numbers. I don't think so. But now Adrian Van Kant, he shows that you can reach like really small values of the Ekman number. So maybe he will revolutionize this field. I don't know. So yeah, anyways, so we want to see how rotation affects the two situations that I showed you before: penetrative convection and layers. So I conducted 2 experiments. One is this one, where you have a convection zone on top of a established stratified region. It's an incompressible box, horizontally periodic, boundary conditions, stress-free. And I impose a heat flux at the top of the box. So I'm cooling down the box over time, just like in Turner's experiments. And I want to take a look at the transport across the boundary, what rotation does to that. So I run simulations with Daedalus at very modest parameters, I would say. The Rayleigh number is about 4 times 10 to the 7, the Ekman 8 times 10 to the minus 5, and the Pratt number and tau was about 0.5. In any event, these convection zone change their size over time, so this is not quite representative, I would say. But anyways, we run those simulations, and these are some snapshots. I think this is the vertical component of the vorticity, if I remember correctly. This is close to the initial state, and then you let this box to cool down over time, and you can see that the convection zone is propagating inwards. This is for the rotating case. So in these plots, I'm showing you some vertical profiles. This is the composition flux, and this is the kinetic energy flux in the vertical direction for the non-rotating case and the rotating case. The stable regions are in pink in these plots. So you can see that for the same heat flux, the composition flux in the rotating case is smaller.
Sorry, Rafa, did you say, is this anelastic, Boussinesque?
No, it's Boussinesque, incompressible, sorry. So you can see that in the rotating case, the fluxes are much smaller than for the non-rotating case.
What are the compositional boundary conditions?
It's insulating, it's zero at the top. For both cases, all of the rotating case and the non-rotating case, they have exactly the same boundary conditions. And parameters. The only difference is that one has rotation and the other one has not. So yeah, it's a factor of 3 or 4, something like that, smaller, both the composition flux and the kinetic energy flux in the vertical direction. And I recall you that from the mixed length theory, the relation between these fluxes was the Rossby number to the 1/2.
Is this time averaged profiles?
I think I time average over 10 convective turnover times or so. It's not a significant average, just to get the soft curves. So yeah, the relation between the fluxes was the Rossby number to the 1/2. And I measured the Rossby number from the flows using the RMS and the size of the layers to compute if this is true or not, if it holds or not. So yeah, I measured 0.065 as the real Rossby number for Daniel. And if you take the square root of that, that is about 1/4. So I think the numerical simulations follows the mixed length at this level. It's not that precise, but it's decent. Also, we track the evolution of the convection zone as a function of time for the two cases, again. And you can clearly see that the rotating case takes way longer to reach the same level within the box. Trust me, or you can see Brad's poster, that you can do analytic calculations for this. You basically, if you know the initial distributions of the density, you can calculate the rate at which the potential energy changes. Because of the mixing, you estimate that, and you said that is equal to the kinetic energy flux with this entrainment parameter. Could be 1, you can measure that, it's fine, it's not relevant for this. But these two are functions of the size of the convection zone. So if you know, you can calculate this easily from the initial profiles. But if you know a prescription for the convective velocity as a function of the size of the layer, such as the ones that you can get from mixed length, the free fall for the non-rotating case, and the ones for, using CIA balance for the rotating case, you can integrate this and get analytic solutions for this, for how the convection zone moves over time. So again, for the non-rotating case, it's T to the 1/2 that is known. And if you use the CIA balance scaling, you can get T to the 512, which is about 0.4 or so, with this prefactor that depends on the rotation frequency. So we conducted fits only to the power, only one parameter, just the power that goes in time for these curves. And we found that it's very close. For the non-rotating case, T to the 4.9, and for the rotating case is T to the 0.4. So from these simple experiments, rotation has an effect on the convective boundary mixing. It delays the propagation of the convection zone because it reduces the kinetic energy flux available. And because of that, the rate of entrainment it's much smaller. We cannot apply this to the gas giants yet because this is Boussinesque, but it would be really nice to conduct similar experiments with density stratification and see how these convective boundaries move over time in more realistic systems. You had a question.
Yeah, what is the ratio between the buoyancy frequency and the rotation frequency?
Oh,
The case you showed.
that is a good question. I don't think I don't have the number.
But it's smaller than 1 or larger than 1?
I don't know. I haven't thought about that. But I think that for Jupiter, n squared is about 10 to the minus 6 or so, and the rotation frequency is whatever you get for one rotation in 10 hours. So you can compare that.
The period of Jupiter is 10 hours.
Right.
The period, yeah, the rotation period.
It's about 1/2 of Earth. Earth is 10 to minus 4, so it's about half of it.
Okay. So n squared is it's smaller than omega, basically.
Well, but what matters? N, right?
Huh?
Not n squared.
So what
It's the ratio of n over omega, not n squared.
Okay.
So both frequencies.
So then it's an order of magnitude difference between the two. Yeah, I don't know how is this for my simulations. Sorry about that. Okay, that was about the entrainment. See, 5 minutes. Okay, I'm gonna go fast. Yeah. So the same, but now let's see what happened to the layers. If rotation reduces the mixing efficiency and prolong the lifetime of the gradient, then maybe the layers don't merge as quickly as in the non-rotating case. So again, we run simulations, same parameters. We initialize the fluid with the right gradients just to develop layers because we want to see the effect on the layers. Okay, those are the parameters. We use Daedalus again, and just as in the other experiment, this is incompressible, and the rotation goes anti-parallel to gravity. Okay. So yeah, how rotation modifies the mixing time of the layers. So this plot is actually kind of nice because it shows you the entire, like a movie in a 2D plot. So this is the vertical position within the box, and this is time, and the color represents the composition. So initially, you start with the linear gradient. Then you excite the double-diffusive instabilities, and you spontaneously form multiple layers, just to what you expect from double-diffusive instabilities. So I have fixed fluxes on each boundary. So eventually what happens is that these layers start to, the other ones start to be dominated by the boundary, by the boundary. They are boundary driven, so they grow and they entrain, they mix the inner layers. Then you reach this situation that we call erosion phase, where the two layers are trying to mix each other, and they don't mix because there is a density jump between the two. But eventually, they are entraining each other, and that density jump goes to 0, and they mix. So that is what happened with the non-rotating case. And in the rotating case, it's roughly the same. You start with the linear gradients, you form the layers grow, merge, erosion phase, and the whole box becomes fully mixed, but on a different time scale. The other difference that I see is that the layers seems to be thinner, maybe, and more fuzzy. I think they are thinner because the velocities are smaller, so they don't have enough energy to grow to the same size of the in the non-rotating case. And the fuzziness could be because of, I don't know, I think could be that since they had to evolve for a longer time, chemical diffusivity in the interface maybe weakened the gradient. It's not as sharp. But in any event, the time scale that takes for the box to become fully mixed in the rotating case is longer. And the erosion phase is actually longer as well. So the fun thing here is that in this kind of states, the dynamics looks very simple, so you can do analytics as well and make some predictions. So that is what we did. So we measured the density jump at the interface in the erosion phase. Just focus on the erosion phase because it's the easy part. And what we found is that over time, this density jump decreases linearly with time, until eventually it crosses 0 and the things mix. So we made some predictions, actually. You can do the same argument, the energy argument that I told you before with the entrainment, but keeping the thickness of the layers to be fixed. And you can actually show that the density jump decreases linearly with time. And you can estimate what is going to be the time scale at which they mix. And that is what we did. And again, this factor of the Rossby number to the 1/2 or minus 1/2 appears. But it also depends on the initial on the ratio of the initial density jumps when they enter the erosion phase.
Yeah, I mean, in the rotational case, do you get a temperature inversion?
Yeah, I think this is right when they become fully mixed, and I think that happened is that you are fully mixed in composition, but there is a thermal gradient across the box that makes the density jump to be actually negative. And it has to be negative, otherwise it's going to be stable. And by this state, things are already fully convective, so the density has to be negative, or 0. No gradient for the non-rotating case, but there is a thermal gradient in the rotating case. That is why I ask in the morning. Okay, anyways, these time scales for mixing are related through the Rossby number to the minus 1/2. We took measurements. I think that from the simulations, we estimate like a 2.11, and the prediction is 2.44. This is cool. This is really cool, but we just ran 2 simulations, so we cannot test this scaling. We need to do more simulations to actually see if it's actually a Rossby number to the minus 1/2. So yeah, the take-home message for this session is that for these simple experiments, rotation does matter for mixing. It matters for the entrainment and penetration of the outer convection zone, and it matters to the layers, to the semiconvective layers. So that is definitely something that should be taken into account. The experiments that I did were in boxes, but I'm moving to spherical geometry, also using Dealus. But the next step, and I think the most significant one, is to add density stratification to the system. Again, because we are trying to understand a system with 10 density scale heights, the mixing happens deeper in the interior, and for that we need global models. So yeah, thanks for your attention, and yeah.